Where do the elements in your smartphone or EV come from? It's a question that invites us to journey to the heart of our modern technology, to the building blocks that power our lives. They're called the rare earth elements, and there are 17 of them, each with its own unique properties and uses. Before we go on, please hit the like button and subscribe to CMX. Let's take a roll call. First up, we have lanthanum, symbol La, and cerium, symbol Ce. They're followed by praseodymium or Pr and neodymium Nd. Next in line is promethium PM and samarium SM. The list continues with europium Eu and gadolinium Gd. Then there's terbium Tb and dysprosium Dy. We've also got holmium Ho, erbium Er, thulium Tm, ytterbium Yb, and lutetium Lu. Last but not least, we have scandium Sc and yttrium Y. These elements might not sound familiar, and you probably won't find them in your high school chemistry textbook, but they're all around you. They're in your smartphone, your laptop, your hybrid car, even your LED lights. They help you connect with the world, drive you to your destination, and light up your nights. But where do these elements come from? Most of the rare earths used in the world are mined from places like Bayan Obo in Inner Mongolia, Shandong and Sichuan provinces in China, as well as Vietnam, Brazil, Russia, India, Australia, Greenland, South Africa, Tanzania, Canada, and Mountain Pass in California in the United States. These places are rich in these elements, hidden deep in the earth, and are already being exploited. The process of mining these elements is complex and requires advanced technology, but yield invaluable results. These elements are essential to our modern lifestyle, driving innovation and powering our most advanced technologies. These are the invisible heroes that power our technology, yet remain largely unknown. But now you know them. You know their names, their symbols, and where they come from. And as we journey further into this fascinating world of rare earth elements, you'll discover why they're so important and why we must protect them from overexploitation. Imagine holding elements in your hand that were once hidden deep within the earth. The tale of the 17 rare earth elements begins millions of years ago, within the molten core of our planet. Here, intense heat and pressure colluded to create these unique substances. Like a master craftsman, the earth forged these elements, each with its own distinct properties. Rare earth elements, except scandium, are heavier than iron and thus are produced by supernova nucleosynthesis, or by the S process in asymptotic giant branch stars. In nature, spontaneous fission of uranium-238 produces trace amounts of radioactive promethium, but most promethium is synthetically produced in nuclear reactors. Due to their chemical similarity, the concentrations of rare earths in rocks are only slowly changed by geochemical processes, making their proportions useful for geochronology and dating fossils. During the 1940s, Frank Spedding and others in the United States, during the Manhattan Project, developed chemical ion exchange procedures for separating and purifying rare earth elements. This method was first applied to the actinides for separating plutonium-239 and neptunium from uranium, thorium, actinium, and the other actinides in the materials produced in nuclear reactors. Plutonium-239 was very desirable because it is a fissile material. The principal sources of rare earth elements are the minerals bastnasite, RCO3F, where R is a mixture of rare earth elements, monazite, XPO4, where X is a mixture of rare earth elements and sometimes thorium, loperite, and the lateritic ion adsorption clays. Despite their high relative abundance, rare earth minerals are more difficult to mine and extract than equivalent sources of transition metals, due in part to their similar chemical properties, making the rare earth elements relatively expensive. Their industrial use was very limited until efficient separation techniques were developed, such as ion exchange, fractional crystallization, and liquid-liquid extraction during the late 1950s and early 1960s. Today, we understand that these elements are far more than just interesting curiosities. They are the building blocks of modern technology, the secret ingredients in our smartphones, electric vehicles, wind turbines, and so much more. They are, in essence, the elements of the future, formed by the past. Where do we find these elements? Let's take a journey around the world. Until 1948, most of the world's rare earths were sourced from placer sand deposits in India and Brazil. Through the 1950s, South Africa was the world's rare earth source, from a monazite-rich reef at the Steenkamp Skraal mine in Western Cape Province. Through the 1960s until the 1980s, the Mountain Pass rare earth mine in California made the United States the leading producer. Today, the Indian and South African deposits still produce some rare earth concentrates, but they were dwarfed by the scale of Chinese production. In 2017, China produced 81% of the world's rare earth supply, mostly in Inner Mongolia, although it had only 36.7% of reserves. Australia was the second and only other major producer with 15% of world production. All of the world's heavy rare earths, such as dysprosium, come from Chinese rare earth sources, such as the polymetallic Bayan-Obo deposit. The Browns Range mine, located 160 kilometers southeast of Halls Creek in northern Western Australia, was under development in 2018 and is positioned to become the first significant dysprosium producer outside of China. In 2019, China supplied between 85% and 95% of the global demand for the 17 rare earth powders, half of them sourced from Myanmar. Kachin State in Myanmar is the world's largest source of rare earths. In 2021, China imported $200 million of rare earths from Myanmar in December 2021, exceeding 20,000 tons. Rare earths were discovered near Pangwa in Chipwai Township along the China-Myanmar border in the late 2010s. As of March 2022, 2,700 mining collection pools scattered across 300 separate locations were found in Kachin State, encompassing the area of Singapore, and an exponential increase from 2016. Increased demand and tightening restrictions on exports from China have led to searches for alternative sources globally. Significant sites under development outside China include Steenkamp Skraal in South Africa, the world's highest-grade rare earths and thorium mine, closed in 1963, but has been gearing to go back into production. The largest rare earth deposit in the U.S. is at Mountain Pass, California, 60 miles south of Las Vegas. Originally opened by Molycorp, the deposit has been mined, off and on, since 1951. A second large deposit of REEs at Elk Creek in southeast Nebraska is under consideration by NioCorp Development Ltd., who hopes to open a niobium, scandium, and titanium mine there. In the UK, Pensana has begun construction of their $195 million rare earth processing plant, which secured funding from the UK government's Automotive Transformation Fund. The plant will process ore from the Longonjo mine in Angola and other sources as they become available. The company are targeting production in late 2023, before ramping up to full capacity in 2024. Pensana aimed to produce 12,500 metric tons of separated rare earths, including 4,500 tons of magnet metal rare earths. Other potential mine sites include the ASX-listed Peak Resources Tanzanian-based Ngwala project contained not only the sixth largest deposit by tonnage outside of China, but also the highest grade of rare earth elements of the six: North Korea, Ehime Prefecture in Japan, the Kiruna area in Sweden, and Wheatland, Wyoming, where in 2024 American Rare Earths Inc. disclosed that its reserves totaled 2.34 billion metric tons, possibly the world's largest and larger than a separate 1.2 million metric ton deposit in northeastern Wyoming. Other mines include the Nolans Project in Central Australia, the Boken Mountain Project in Alaska, the remote Hoytas Lake Project in northern Canada, and the Mount Weld Project in Australia. Overall, China processes about 90% of the world's REEs and 60% of the world's lithium. As a result, the European Union imports practically all of its rare earth elements from China. REEs are scattered across our planet, reminding us that we are a world connected, not just by technology, but by the very elements that make up the earth beneath our feet. How do we extract these elements from the Earth's crust? It's a process as complex as the elements themselves. In the world of mining, it's not just about digging a hole and pulling out the treasure. The process of extracting rare earth elements is a symphony of science, engineering, and sheer human determination. The first step in this intricate dance is exploration. Geologists study the Earth using a variety of tools and techniques to locate promising deposits of these elusive elements. Once a potential site is identified, it's time for extraction. This usually involves a process known as open-pit mining, where a large hole is dug into the earth, often several kilometers wide. The material removed, called overburden, is set aside, revealing the ore beneath. But it's not as simple as picking out shiny rocks. Rare earth elements aren't typically found in concentrated veins like gold or silver. Instead, they're usually scattered within other minerals, making them a challenge to isolate. So, the ore is crushed into a fine powder and mixed with water to create a slurry. This mixture is then treated with chemicals in a process known as flotation, which separates the rare earth minerals from the rest of the ore. Now you might think we're done, but we're only just getting started. The separated minerals still contain a mix of different rare earth elements, and each one needs to be isolated. This requires a process called solvent extraction, where the minerals are dissolved in a series of chemical baths. Each bath is designed to pull out a specific element, leaving the others behind. Finally, the isolated elements are purified, often through a process of heating and cooling known as calcination. The result is a pure rare earth element, ready for use in everything from smartphones to satellites. But remember, each step of this process requires careful planning, significant resources, and a deep understanding of the Earth's geology. It's not an easy task, but it's one that humans have mastered over centuries of trial and error. It's a testament to human ingenuity and persistence that we've found ways to coax these elements from the ground. Why should we care about these elements? Their importance cannot be overstated. Indeed, these 17 rare earth elements are not just rare, they are incredibly significant. They are the silent facilitators of our modern world, the unseen forces that power our technology, energy, and medical industries. Take a moment to consider your smartphone. It's a marvel of technology, isn't it? But did you know that your phone wouldn't exist without these rare earth elements? Elements like lanthanum, neodymium, and praseodymium are vital components of your phone's miniature circuits, touchscreen display, and even its vibrant colors. But their impact extends far beyond the realm of personal electronics. In the energy sector, rare earth elements like neodymium and dysprosium are crucial to the production of high-strength magnets used in wind turbines and electric vehicles. These elements are key players in our pursuit of sustainable, clean energy. And let's not forget the medical field. Gadolinium serves as an excellent contrast agent in MRI scans, enabling doctors to diagnose and treat a multitude of diseases. Europium is used in cancer treatments, and samarium provides relief from the pain of bone metastases in patients with certain types of cancer. These elements are even sprinkled throughout our daily lives in less obvious ways. They're in the catalytic converters that reduce harmful emissions from our cars, in the batteries that power our laptops, and in the phosphors that light up our flat-screen TVs. But perhaps the most important thing about these elements is that they are finite. They aren't spread evenly across the globe, but are concentrated in a handful of places, like the mines of Bonobo in Inner Mongolia, Shandong province, and Sichuan province in China, Vietnam, Brazil, Russia, India, Australia, Greenland, South Africa, Tanzania, Canada, and Mountain Pass in California in the United States. We cannot afford to waste these precious resources or take them for granted. They are essential to our modern life and our future. These elements are the unsung heroes of our modern world. However, the extraction of these elements comes at a cost. The quest to unearth these 17 rare earth elements is not without its collateral damage, most notably on our environment. The mining process, while necessary for our technological advancement, has a profound impact on our planet's health. Let's take a moment to understand just how significant this impact is. Mining is an invasive process. To access these elements, vast amounts of earth need to be moved, resulting in extensive land degradation and habitat destruction. Forests, rivers, and wildlife habitats are often decimated to make way for mining activities. This destruction of natural habitats can lead to loss of biodiversity, affecting the intricate balance of ecosystems. Moreover, the extraction process itself can lead to serious pollution issues. The rare earth elements are often found in ores that contain radioactive elements like thorium and uranium. When these ores are processed, harmful radioactive and toxic waste is produced. Without proper waste management, this can contaminate the soil, water, and air, posing severe health risks to local communities and wildlife. The situation is further aggravated by the fact that rare earth elements are, as their name suggests, rare. This means that a lot of ore has to be processed to extract a small amount of these elements. The larger the volume of ore processed, the greater the environmental impact. And let's not forget about the energy consumed in mining and processing these elements. Mining is an energy-intensive process, contributing to greenhouse gas emissions and thus global warming. Yet, it's important to remember that these elements are vital for our modern world. They are the backbone of our technology and renewable energy solutions. So, the question arises, how do we balance our need for these elements with the need to protect our environment? The answer lies in sustainable mining practices, efficient recycling, and the development of alternatives. We need to mine responsibly, process efficiently, and recycle effectively. And we must continue to invest in research to find alternatives to these elements. Our quest for progress should not come at the expense of our planet. Let's make sure that as we move forward, we don't leave our environment behind. What does the future hold for these elements? A question that brings us face to face with the reality of our reliance on the 17 rare earth elements. As we look ahead, it's clear that our need for these elements is not going to diminish. In fact, it's likely to increase as technological advancements continue to skyrocket. So where do we go from here? How do we ensure that our need for these elements doesn't come at the expense of our planet? The answer lies in creating a sustainable future through innovative practices in mining and recycling. First, let's tackle sustainable mining. Today, new techniques are being developed to make the mining process less harmful to the environment. These involve reducing water and energy usage, minimizing land disturbance, and cutting down on waste generation. Additionally, there's a push for stricter regulations and enforcement to ensure mining companies adhere to these sustainable practices. And then there's recycling. Currently, the recycling rate for rare earth elements is less than 1%. That's right, less than 1%. Clearly, there's a massive opportunity here. By developing efficient recycling processes, we can not only reduce the demand for freshly mined elements, but also lower the environmental impact. Think of it as a two birds, one stone kind of situation. Finally, there's the exciting prospect of finding new sources of these elements. Research is underway to explore untapped resources like deep-sea mud, which is believed to be rich in these elements. Imagine a future where we can extract these elements without disturbing our precious land ecosystems. Now that's a future worth striving for. So as we stand at the crossroads of need and sustainability, we must make a choice. A choice that will determine the future of not just these 17 elements, but of our planet as well. Our actions today are writing the future chapters of the rare earth element story. It's a story that we have the power to shape, to mold into a narrative of sustainability, responsibility, and progress. The future of these elements is in our hands. Let's ensure we handle them with the care they deserve. Now that you know the importance of these elements, what can you do? That's the question we all need to ask ourselves. The answer, believe it or not, lies in the small actions we take every day. Even the most seemingly insignificant choices can have a profound impact on the world around us. Let's start with something as simple as electronics. Our smartphones, laptops, and other devices are packed with rare earth elements. When we're done with these devices, where do they go? Often they end up in landfills, their precious components wasted. But if we take the time to recycle our electronics properly, we can help recover these valuable resources. In fact, recycling just 1 million cell phones can recover nearly 25,000 pounds of rare earth elements. And it's not just about recycling, it's also about making conscious choices about what we buy. By supporting companies that prioritize sustainable practices, we can create demand for responsibly sourced rare earth elements. This means looking for technology manufacturers that are transparent about their supply chains and committed to minimizing their environmental impact. It might take a bit more effort, but it's a small price to pay for preserving our planet. Moreover, we can raise awareness about the importance of these elements. Share what you've learned today with your friends, your family, your colleagues. Encourage them to recycle, to choose sustainable products. The more people know, the more they can take action. Remember, our actions today will shape the world of tomorrow. We have the power to ensure the sustainable use of these elements, to protect our environment, and to secure a bright future for generations to come. The rare earth elements are not just resources, they're part of our world, part of us. We have a responsibility to care for them, just as we do for every other part of our planet. So let's make a pledge. Let's commit to being more mindful of our choices, to thinking about the broader impact of our actions, to doing our part in preserving these precious resources. Together, we can ensure that these elements continue to power our world for generations to come. We've journeyed from the depths of the earth to your smartphone screen, a journey that has taken us through 17 rare and precious elements. They are lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, ytterbium, lutetium, scandium, and yttrium. Each one unique, each one essential in its own way. These elements, hidden deep within our planet, are the unseen heroes behind our modern world. They make possible the brilliant colors on our screens, the powerful magnets in our technologies, and the efficient batteries that power our devices. They are the silent partners in our quest for progress, advancement, and innovation. The journey of these elements is a global one, from the mines in Inner Mongolia to Shandong and Sichuan provinces, and beyond to Angola, Vietnam, Brazil, Russia, India, Australia, Greenland, Malaysia, South Africa, Sweden, Tanzania, Canada, and Mountain Pass in California, United States. Each location contributing its share, each mine a link in a chain that spans the globe. Yet as we've seen, mining these elements is not without its challenges. It's a process that must be handled with care, a delicate balance between meeting our needs and protecting the environment. Our pursuit of these elements must be tempered by our responsibility to the planet, as well as those who may be forced to mine them. So, as we look to the future, the importance of these 17 rare earth elements only grows. They will continue to drive our technological advancements, fuel our innovations, and play a key role in our quest for sustainable solutions. We must continue to utilize them responsibly, ensuring they remain a resource for generations to come. Next time you use your smartphone, laptop, or EV, remember the global journey and the unseen heroes that make it possible. These elements, these tiny, unseen particles, are the backbone of our modern world. They are the silent witnesses to our progress, the secret, priceless ingredients in our recipe for advancement. Thanks for watching. Please hit the like button, comment, share, and subscribe to CMX for more groundbreaking content.